This is our video for related rates. Related rates to me is an extremely interesting topic. It is the day when calculus gets meaning behind it. It's really exciting. So anyway, to introduce this to you, calculus, we know, is the study of continuous change. Calculus gives us a language to describe change. So calculus describes the world, the changes that are happening in the world. It is important to know, we've been dealing with dy dx here for a couple of weeks, and it's important to know that there is actually real meaning behind this. It actually is the instantaneous rate of change of y with respect to x. It's a language for describing change. So dA dt is the instantaneous rate of change of a with respect to t. So it is the way that a is changing over t. Okay? T, for related rates problems in general, our independent variable is going to be time. So you're going to have a lot of t's in there. It's going to be d something dt. All right? Most of the time, not all the time. So when you're doing these problems, ask yourself, what are you actually trying to find? And then ask yourself, how are you going to do it? You're given information. How are you going to answer the question? So let's begin. Let's do some problems. A pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. Okay? The radius of the outer ripple is increasing at a constant rate of 1 foot per second. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. They are giving us information there. It's a rate, so I know it's a derivative. That is the derivative of what? It's the derivative of the radius with respect to time. I know it's with respect to time because of that right there. 1 foot per second. Feet per second. Okay? So dr dt here is 1 foot per second. All right? When the radius is 4 feet, find the rate at which the area of that circle is changing. So what are we trying to find? The rate that the area is changing. So we're trying to find dA dt when the radius is 4 feet. So when the radius is 4 feet, that's what we're trying to find. Okay, do we have an equation that relates area with radius of a circle? We sure do. The equation is A is equal to pi r squared. That is the equation that relates the area with the radius of a circle. We are looking for dA dt. So I know I need to come into this equation and take the derivative of both sides with respect to t. So I'm going to rewrite this, leaving myself a little room, and we're going to take the derivative of both sides with respect to t. On the left-hand side, we will have dA dt. The derivative of a is 1 dA dt. Little implicit differentiation. The derivative of pi r squared is 2 pi r dr dt. 2 pi r dr dt. Derivative of both sides. A little implicit differentiation there. Okay, we took the derivative. Now all we need to do is plug in what we know. We want when r is 4. When r is 4 feet, dA dt will be 2 pi times 4 times dr dt. What was dr dt? Well, dr dt was 1. And so this is 8 pi. What would be the units there? What would be the units there? They didn't ask us for units, so I don't have to give them the units. But to get units, I look here and I look here. That will give me the units. What would units of area be? Well, if the radius is in feet, then the area will be in feet squared, or square feet. What are units of t? Seconds. They didn't ask me for units, but if they had asked me for units, I would give them feet squared over seconds. Units of A divided by units of t. Okay, let's do another one. A 13-foot ladder is leaning against a wall. This ladder is 13 feet long. Is it changing? Is the length of the ladder changing? No, it's not changing. So I'm going to put 13 in here in pen, and it's there. It's not changing. Suppose that the base of the ladder slides away from the wall at a rate of 3 feet per second. The base of the ladder is sliding, it's slipping away from the wall at a rate of 3 feet per second. That's pretty fast. 3 feet per second. How fast is the top of the ladder sliding down the wall? How fast? We're looking for a rate. How fast is the top of the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? You're going to be tempted to put 5 right here. Don't do it, because that 5 is changing. True? The ladder is slipping. So I'm going to label this with a variable because it is changing. Anything that is changing gets a variable. Anything that is constant gets the number. Okay? This is also changing, this distance, because the top of the ladder is sliding down the wall. So I'm going to call that distance y. I usually call any horizontal distance x, any vertical distance y. So that's how I'm going to label that. All right, so they gave us this 3 feet per second. That was the rate. That was the rate that the base of the ladder was sliding away from the wall. So that is our dx dt. Dx dt is equal to 3 feet per second. What are we looking for? We're looking for how fast is the top of the ladder sliding down the wall. So we're looking for dy dt when what? When the base is 5 feet from the wall. So when x is 5. So this ladder is slipping, it's changing. The ladder's not changing, but x is changing. Y is changing. So we're looking for what is the rate that it's changing when x is 5. That's what we're looking for. So we're going to begin by getting an equation that relates x and y. Give me an equation that relates x and y. Why do I want x and y? Because I want y, I want dy dt, and I'm given dx dt. That's why I need an equation that relates x and y. Well, this is a right triangle, and I know that every right triangle obeys the Pythagorean theorem. So x squared plus y squared must be 13 squared. That is true all the time. I don't care how far this ladder slips, that's true, because this is always going to be a right angle. Okay, so there's my equation, and I'm going to come in here and I'm going to take the derivative of both sides with respect to t. Why with respect to t? Because that's exactly what we want. So derivative with respect to t on both sides. The derivative of x squared with respect to t is 2x dx dt. The derivative of y squared with respect to t is 2y dy dt. The derivative of 13 squared with respect to t is 0. I can divide both sides by 2 and the 2's will be gone. I think I'm going to go ahead and do that. Simplify our equation. Okay. Now we're going to plug in what we know. We know that dx dt is 3, and I want x to be 5. So when x is 5, when x is 5, I'm going to have 5 dx dt plus y. Do we know what y is? Well, when x is 5, what will y be? Again, we can use the Pythagorean theorem here, or you can just know that this is a 5, 12, 13 right triangle. And either way, if you need to go and use the Pythagorean theorem, do it. But when x is 5, y is 12, so I'm going to have 12 dy dt, that's what I'm looking for, is equal to 0, and now I just solved that for dy dt. So we're going to subtract 15 to the other side and divide by 12. Oops, almost put an X there. Negative 15 divided by 12, which is negative 5 over 4. Does it make sense that that is a negative number? We got a negative number for that rate. A negative number for this rate tells me that y is getting smaller. Is y getting smaller? Yes, as the ladder falls down, y is getting smaller. So it's a good thing we got a negative rate, otherwise I know our answer would have been wrong. Okay? So they didn't ask me, oh, they did ask me for units. Never mind. They did ask me for units. What will be the units there? Well, we'll need units of y divided by units of t. What will units of y be? Well, units of x were in feet, so units of y must be in feet. What are units of time? Units of time were seconds again. Feet per second. Okay? If they ask you for units, you must give units. Let's do another one. An empty cylindrical barrel fills with rainwater during a storm. The circumference of the barrel is 5.5 feet, and the height of the barrel is 4.2 feet. Okay? At the peak of the storm, the depth of the rainwater in the barrel is 3.7 feet and is increasing at a rate of 0.5 feet per minute. Okay? What are they telling us? The depth is 3.7 feet and is increasing at that rate. So this rate will be d something dt, right? D what dt? What will be the depth? Here's the formula for the volume of a cylinder. What's the depth? Well, the depth is h. So dh dt is 0.5 feet per minute. Okay? At that time, what is the rate? At what rate is the volume increasing? So rain is coming in, the volume's increasing, the height's increasing. Is the radius increasing? No, the radius is staying the same, isn't it? The radius is staying the same. But I do want dv dt. I want dv dt at that exact moment when the height is 3.7 feet. So actually at h equals 3.7 feet. That's what I want. Okay? So the radius here is not changing. Well, what is the radius then? If it's not changing, what I need to know what it is because it's right there in my formula. My formula is v is equal to pi r squared h. V is changing, H is changing. R is not changing. R is a constant. And anytime I have a constant, I'm going to put it in there. So what is it? The circumference is 5.5 feet, right? Well, the circumference is 2 pi r, and that is 5.5 feet, right? So if I divide by 2 pi, r will be 5.5 over 2 pi. Yeah? So that's a constant. Those are all numbers. 5.5 is number, 2 is number, pi is number. R is 5.5 over 2 pi. So I'm going to put that in place of r. So now I have V is equal to pi times 5.5 over 2 pi squared h. That's what I have there. Yeah? So, okay, I could simplify that, but you know what? I think I'm going to just leave it like that. This is just a number, this is just a number. Do those pi's cancel each other out? They do not. They do not cancel each other out because this is being squared. We could clean it up. If I wanted to, I could clean that up. We really don't have to. But if I clean that up, 2 squared is 4. This would be pi squared. One of these pi's is going to reduce with that pi, and I'll be left with just a single pi down in my bottom. Okay? All right. I don't have a calculator, so I'm not going to clean that up anymore. So whatever, that's fine. Not that I would have to have a calculator for that, but whatever, it's okay. Alrighty, so what are we looking for? We're looking for dv dt. So I'm going to come in here and I'm going to take the derivative of both sides with respect to t. So I'm going to come right here and take the derivative of both sides with respect to t. Squeeze that in front. Do not put this in the back. It'll make you look like a fool. So keep it up in front, even if you have to squeeze it in. So dv dt is equal to, okay, this is just a number. It's like a 7 or 2 or something. It's just a number. So what's the derivative of a number times h? Just that number. Just that number. dh dt. Don't forget your dh dt. Little implicit differentiation there. Little chain rule there. Okay. Time to plug in. So we're plugging in 3.7 for h, but we don't have an h to plug it in for. So if you want to say when h is 3.7 feet, you can, but this is going to be true regardless of when h is, what the value of h is. This is going to be true all the time. So not just when h is 3.7, but all the time. Well, you know what? The way they worded this problem, I might just say it anyway. When h is 3.7 feet, when h is 3.7 feet, dh dt is this. And that the way they wrote it, I get the feeling that this might not be constant. So I'm just going to write this and that way I can put 0.5 in for h. So, or in for dh dt. So dv dt will be 5.5 squared over 4 pi times 0.5. All numbers, this is an FRQ, so I really don't have to simplify this. Therefore, I'm not going to simplify this. Did they ask me for units? They did not ask me for units, so I am done with this problem. I'm done. However, what if they had asked for units? If they had asked for units, I would need units of V over units of T. What would units of V be? The height is in feet, so volume would be feet cubed. Units of time, time is in minutes. Feet cubed per minute. Okay? Alrighty. Let's do another one. This time we have a cone. Alright. Water runs out of a conical tank. Water is running out of a conical tank at a rate of 2 cubic feet per minute. It's a rate, so I know it's d something dt. D what dt? Cubic feet per minute. Cubic feet, it's got to be volume per minute, so it's got to be dt. Cubic feet per minute. Okay, what is that? It's a constant rate of 2, but water is running out. Is V increasing or decreasing? The volume is going to be decreasing. So we need to make that a negative 2 cubic feet per minute. All right, they would not say water runs out of a tank at a rate of negative 2 cubic feet per minute. They are not going to say that. It doesn't flow. It's not how we speak. So you have to interpret that. You have to be the one to put the negative there. The radius at the top of the tank is 8 feet, and the height of the entire tank is 10 feet. So this is, I can see I have some units wrong here, but we will fix that and just get rid of the units right there. They must have been, oops, that's not an 8, that's a 10. Feet. Okay. All right. How fast is the water level decreasing? How fast is so we're looking for a rate, is the water level, that's the height of the cone, decreasing when the water is 4 feet deep? So we're looking for dH dt when the depth is 4 feet. That's what we're looking for. Okay. The volume of a cone, I need to fix that on your notes. The volume of a cone is 1/3 pi r squared h. Okay. Is the volume of the water changing? Yes. Is the radius of the water changing? As this goes down, water's running out here. As this goes down, is the radius going to be changing? Yes. Is the height changing? Yes. All of them are changing, right? So they're all changing. Okay. I can think of 2 good ways to do this problem, but I'm going to show you the way that I always do these. So, over here on this cone, do you see this from the top of the cone? Do you see this little triangle there? It's actually not a triangle, but it's that part of the cone. And do you see this one? Those are similar triangles. Those are similar triangles. Therefore, therefore their sides are proportional to each other. So R is to 8 as H is to 10. R is to 8 as H is to 10, right? And that will be true no matter what the water level is. That's true all the time, right? So I know that R is equal to 8 over 10 H, which is 4 over 5 H. Which means, since I want dH dt and I have dV dt, since I want dH dt and I have dV dt, I want to get only h's involved if possible. So I want to kind of replace R with something with h's in it, and now I can, because R is 4/5 h. So I'm going to replace this R with 4/5 h. And now I have all h's, and I can clean this guy up. So I'll have v is equal to 1/3 pi times 16 over 25 h squared times h, keep on cleaning up, 16 pi over 75, make that into one fraction, yeah, h cubed. Now this is extremely easy to take a derivative of. So that's why I went through that process. The other way that I said that you could do is you could just leave r in it and use the product rule here. When you're taking the derivative, use the product rule. You're still going to have to come over here and get, the thing is you're going to get a dr dt, and so you'll need to come over and get dr dt that way. This way is probably the easiest way. Okay, coming in, time to take a derivative. So I'm going to take the derivative of both sides with respect to t. dv dt is 3 times this. It's going to reduce that 75, make it back to the 25, so we'll have 16 pi over 25 h squared dh dt. Little chain rule there. The derivative of h cubed is 3h squared times the derivative of h, which is dh dt. Okay? All right, time to plug in. So when h is 4, when h is 4, okay, dv dt was the -2. We're squaring h dh dt. Okay, and now we're solving this for dh dt. So I'm going to multiply both sides by 25 and divide both sides by 16 pi times 16. Okay, I write it like that because I can just leave it like that. I was going to reduce, but I think I'm just going to leave it like that. Okay, did they ask me for units? No, they did not. What if they had? What would the units be? Units of h over units of t. Units of, the volume was in feet cubed per minute, so units of h would be feet. Units of time would be minutes. If they had asked me for units, I would say feet per minute. Let's do another one. A 6-foot tall man walks at a rate of 5 feet per second away from a 16-foot tall light pole. The man is 6 feet tall, and that's not going to change. He's going to stay 6 feet tall throughout this whole problem. He walks at a rate of 5 feet per second away from a 16-foot tall light pole. Okay, the light pole is 16 feet tall, and that's not going to change in this problem. This is a rate. We'll deal with that in a second. When the man is 10 feet from the base of the light pole, at what rate is his shadow lengthening? I'm going to label this x because that's changing. dx dt is this 5 feet per second. dx dt is the 5 feet per second. That's the rate that he is walking. We want the rate that the length of his shadow is lengthening. So I'm going to give this another variable. I'm going to call it s. My printed s's tend to look like 5s, so I try to use cursive s's when I think of it. So at what rate is the length of his shadow changing? We're looking for ds dt. When he is 10 feet from the base of the light pole, so when x is 10. At what rate is his shadow lengthening? Okay. I need an equation that relates x and s. So what will that be? Well, where is the shadow? That's true, right? That's how a shadow is formed. If the light is coming from the light pole, I'm assuming it is here. Okay, again, you guys, we have similar figures, similar triangles. That triangle and that triangle are similar. I could use like side angle side or whatever to show that they are similar. So we can set up proportions, okay? Okay, let's say this side is proportional to this, true? Yeah? So 6 is to 16 as this leg, S, is to the whole thing, S plus X. True? Okay. I'm going to cross multiply here. I'm going to have 6S plus 6X is equal to 16S, which means that 6X is equal to 10S. Divide both sides by 2 to clean it up slightly. 3X is 5S. I'm looking for ds dt, so I'm going to come in, take the derivative of both sides with respect to t. 3 dx dt is 5 ds dt. When x is 10 feet, we'll have 3 times dx dt was 5, is equal to 5 ds dt. So ds dt is equal to 3. Did I do that right? I think I did that right. I'm questioning that. Yeah, it's right. Okie doke. Units would have been feet per second again. All right, last one here. As a snowball rolls down a hill, it maintains its spherical shape such that its volume is increasing. Its volume is increasing at a rate of 25 cubic centimeters per second. So dV dt is positive because it's increasing 25 cubic centimeters per second. At what rate? At what rate is its radius increasing? When its circumference is exactly 33 centimeters. So we're looking for dr dt when the circumference is 33 centimeters. Okay? Well, our formula for volume is 4/3 pi r cubed, volume of a sphere. Okay? With radius r. So, I'm given dV dt. I want dr dt. I have no extra variables. I'm ready to come in here and take the derivative of both sides with respect to t. dV dt is equal to 3 times 4/3 is just 4. So 4 pi r squared, then chain rule, dr dt. Okay? Time to plug in. We want circumference to be 33. When c equals 33, Well, when C is 33, what is R? Because I need to plug something in for R. So we'll have 2 pi R is 33. So R is 33 over 2 pi. So when that is true, dv dt, which is 25, will be 4 pi times 33 over 2 pi squared dr dt. And now my computer is running low again. Let me plug it in. Sorry, hang on. Okay. So when C is 33, this is dr dt. I'm going to divide, so let's see. I'm going to, well, let me go ahead and clean this up. We'll have 33 squared, I'm not going to square it, divided by 4 pi squared, right? The 4's are going to cancel each other out. One of these pi's reduces with that pi. This remaining pi I'm multiplying to the other side, and then I'm going to divide by the 33 squared. And I'm going to stop there. That is sufficient. What would units be? They didn't ask me for units, so I don't have to give them, but what would units be? The volume, everything is in centimeters, so radius will be in centimeters. Time was in seconds, so if they had asked me for units, it would be centimeters per second. Okay. Related rates problems are lots of fun. They really are. They get interesting, they get a little challenging, but this is when calculus really comes alive. Okay? We are talking more and more about the meaning behind what we're doing with calculus.